continue our story. Test. Yeah, assuming, yeah, I guess you guys have been responding to me, so I assume my sound is okay now. And we are continuing the story about gravitational potential energy, right? So before we discuss potential energy, I have shown you how to write down the Newton's law in the vector form, right? So in high school, usually they teach the easy way is just to look at the magnitude. And then most of the time, even for us now also, once we get the magnitude, the direction, you can figure it out yourself later, right? And right now, I will teach you the way to, a more efficient way to describe direction is by using the unit vector. So the unit vector is cos theta sine theta, right? So it is this vector with an x and y component that is always pointing away from the origin. So if I want to, this is the mass, if I want to draw the coordinate system where my big M is at the origin, then in this problem I want to look at the force on the small m. So what is the force acting on this m? So the force is over here, so therefore it's pointing from here towards the big M, which is the origin. Therefore I got the direction is negative r, right? So the magnitude is this number and the direction is pointing towards the origin, right? So yeah, right, so the magnitude, so this one is just to remind you of what we were talking about in the previous class, and then the direction is towards the origin, right? So towards the origin, so that's why there's a negative sign over here. Okay, so so this is how we write down the direction. So hopefully everyone is very clear with this right now. So what I want to do for this chapter, we kind of started this a bit already, right? Remember in the Monday's class, before we ran out of time, is to want to calculate the work done. So I want to calculate m, right? So the mass m, initially at distance r1, and then later at position distance 2. So let me draw this picture again, right? So initially it's at r1, so it's small m, and then initially the distance is r1 here, and then later at a later time it will come to here, so r2. Okay, so this is initial, and then this is final, right? So the mass m has moved from position at distance r1 and it moved towards r2. So I want to calculate what is the work done during the process. So there's only one force acting on m, which is the gravitational force because of this big M over here. So this big M is exerting a gravity on this part, right? So I want to find the work done by gravity. So the work done by gravity, as always, is the formula, the integral of F with respect to dr, right? So, and then in the previous class, let me try to show you again, because this is a new concept for most students, is how to calculate dr vector, right? So F vector is this vector, right? So that one we know already. And then I want to take a dot product with the dr vector. So what is the dr vector? So let me remind you what is r. R is the position vector. So the position vector is a vector that describes the location of my object. So it's the position of m, right? So position vector is telling us the position of m. And dr means it is the change in position of m, right? So, but we're going to do that later. But the r first is position of m is, of course, we're going to have some x coordinate and then have some y coordinate, right? So this is my xy axis. So of course, it's going to have some x and y coordinates. And for this case, I want to use the polar coordinates. Therefore, instead of x, the component is r cos theta I. Okay. And then r sine theta j. Okay, so this is my position vector. Okay, so then I want to look at the changes in position, right? And I want to look at the infinitesimal change. So infinitesimal change means I want to find what is the changes of r, and usually we write this as a differential. Okay, so what is this? So changes in this is just like looking at the change on the right hand side. So left and right hand side should be the equal. So what is the change in r cos theta, and what is the change in r sin theta? Okay, so everyone follow so far, right? So r is a variable, theta is a variable, but in this case, right, in moving from r1 to r2, theta is constant. So only the radius changed. Okay, so only the radius changed. So theta is constant. That means cosine theta is a constant. So dr theta is just that means differential is, we can do it like derivative. So we got a dr cos theta. Cos theta is constant, so we don't need to do anything. And then I only change the r, and then sine theta j. Okay, so dr is a quantity that I can factorize, so I can factorize this out, and then I got cos theta I, and then sine theta j. Okay, and then we recognize something familiar, is this one is again my expression for my unit vector. So this is r. So from here I written my equation for r vector. What is the changes in position as my mass m moves from distance 1 to distance 2? Right, so it's moving only in the radial direction. So I got r hat dr. Okay, so this is how we write down a vector. Okay, so the vector is just the direction is r hat, right? And then dr is the change in the distance. Okay, so yeah, so that is our expression for the change in the position. Okay, so I have found how to write down dr already, and then the f vector is already here. So what I'm going to do is I will take the dot product and try to find the work done. Right, so to find the work done is the following. Okay, so for the work done, my f vector is the integral of f. Hang on, work done is w. So f dot dr, right? And I have shown you how to write down the f. This is the force due to gravity. Okay, so it's r hat negative, and then dot dr is this whole thing, right? So this is r hat dr. Okay, so I have a minus sign, and then I got integral gmm over r square, and then r dot r dr. Okay, what is r dot r? R dot r is just equals to 1. So my work done is now come to this calculation, gmm over r square, the integral with respect to r. Okay, so yeah, does everyone follow so far how to get from here to here, right? Usually I think in the high school they straight away give you this expression. I'm just explaining to you where this formula come from, right? So it's just the integral. You can actually this is just the integral of the scalar with respect to r only. Okay, so let's see who is confused. r equals to 1. Yeah, if you don't, you can work it out and see lah. So why is r hat is this, right? So r hat is this. So what is r dot r? Right? So it's cos squared plus sine squared is equals to 1. Yeah. So yeah, so that's why I think must remember there's a r hat, and then there's a r vector, and there's too many r's everywhere. That's the problem. Okay, so now that we have expressed as a, so I have expressed my problem as an integral with respect to r. So now I know how to put in the limits. So my object is initially at distance 1, little m is initially at r1, right? And then at some later time it's going to be at position r2. So we just need to perform this integral, right? Very simple. So just integrate this. So integrate 1 over r squared. This is where we have to be careful, right? So integrate 1 over r squared, I got gmm, and then it will become r, right? And then there's a minus sign. Outside there's another minus sign. Okay, so don't forget, so minus minus, they will cancel each other later. And then after you integrate already, GMM are always constant, nothing there. So the limit is from R1 to R2. So these two negative signs cancel each other. So the work done is just GMM over position 2 minus GMM over position 1, right? And now we can see the conservation of energy. So this is the expression for the gravitational potential energy, right? So this one we defined as the gravitational potential energy okay, so it is a potential energy, right? It is we call it U again, and we define it with a minus sign. So I got Gm small m over R. Okay, so our definition comes with a negative sign. So gravitational potential in this case is always a negative number, and it goes to 0 at R going to infinity. All right, so this is my gravitational potential energy. So from here we found that this is my potential energy at position 2, negative, minus potential energy at position 1. Okay, and furthermore, remember this W, we got the work energy theorem. Right, so work energy theorem. So this is the change in potential kinetic energy. This is negative U2, and then this is plus U1. So if I bring this over, I find that K2 plus U2, and then this is K1 plus U1. Okay, so this is my conservation of energy again. All right, mechanical energy in a gravitational system. If at the length R, no, not R0, at the radius of the object. Yeah, because R0 is the center of the planet. Yeah, so a typical situation is, let's say you're on Earth, right? Then the radius of the Earth is, we call it big R, and then I forgot what's the number, 6,000 something kilometer, right? And then over here, so this is land, and then my position is over here. So if let's say I launch a satellite, right, or some rocket, whatever, right? Initially at, I don't know, the distance is this is R1. Then let's say it's moving at some velocity u, so the kinetic energy is half m u square, and then the potential energy is negative gmm over some number square, right? Some number here, and then over here is, if I land here, then the velocity is some number, and then the potential energy is gmm over big R, like this. Okay, so this I guess you get my idea, right? So if there's no other external force, then energy is conserved, because gravity is a conservative force. Gravity is a force that doesn't depend on time or direction. It only depends on position. If it only depends on position, it's a conservative force. We can define the potential energy, and once we have potential energy, we can use conservation of energy to calculate. Near the core, the potential energy will become very big. Actually, no. So because this equation is for outside the object. If you are inside the object, right? So remember, potential energy is by integrating the function for the force. So what are the forces acting inside here? If I'm inside the planet, right? If I'm inside the planet, then the gravity will be weaker already. So the potential energy will change back accordingly. You know what I mean? Yeah. So for now, we will ignore what happens inside the planet, but the answer is no, it won't become very big. Yeah. Because we still need some kind of multivariable calculus to solve this problem for inside the planet. We will do this in the electromagnetism. It's not 9.81. So if you're inside the Earth, right, the acceleration due to gravity is less than 9.81. Okay. So yeah, as I said, right, to solve this problem inside the Earth is more complicated. But let's just imagine if you are somehow right at the center of the Earth. Right, if you're right at the center of the Earth, right, what is your net force acting on you? So there's mass everywhere around you. So all the mass, remember, have gravity. So if you're right at the center, right, you realize that the force is actually 0, because if you're right in the middle, this part will pull you in one direction, then the other part will pull you in the other direction, so the net force cancel each other out. So inside the center is actually 0 force. Yes. The plan most likely is I will teach electromagnetism, and I guess the reason why you're asking is, this one, we will solve this problem in electromagnetism, right? Because Coulomb's law is very similar to the Newton's law, and we will actually solve this in more detail when we go to electromagnetism. So we will worry about this, like what happens inside object in electromagnetism. So for now, we focus on everything that is outside, which is the easier problem to solve. Okay, so in any case, if as long as we're outside the planet, right, we have the conservation of energy equation. So K2 plus U2. So if I write down explicitly, right, it is half whatever the mass of the object we are talking about, and then the velocity at 1 square. Potential energy has a minus sign, Newton's constant, the planet mass, small m, over the position, r1, and then at a new location, I will have a new velocity, and then I got gmm over r2, new position. Okay, so this, so basically, this is the equation for conservation of energy for an object in gravity that is initially at this position and later at some other position. Okay, so let us solve one example. We don't need this already, right? Okay, so example 7.2.1, right? So in this example, it's just to see how we use the formula. So in examples, right, I'm writing it down. So 7.2.1, a rocket is launched from the surface of the Earth with an initial velocity u. Okay, so luckily you asked, on the land, the r is not 0. On the land, r is on the surface of the Earth with some initial velocity u, right? And then I want to reach a distance of 2r. So I want to reach a distance of 2r. 2r. So this is another r. So this distance is 2r, and then I want to have the final velocity. So what is the minimum velocity u in order to the function 7.26? Oh, you're right. Typo. There's a square, right? Shouldn't have a square there. I'll fix it later. But you know what I mean, right? Okay, so I got this. Anyway, as it launched, I will solve the problem here. Okay, so I have the conservation of energy, right? So I have half m, initial position is u square, initial speed is u square, and then initial position is at big R on the radius of the planet, and then I want to reach a final velocity, and the final position is 2 times big R. Okay, it's like this. So as you can see, right, if to obey this equation must be satisfied for conservation of energy. So if I start off with some initial velocity that is faster, the speed, the kinetic energy at a later time, I can be higher, right? So I want to find a minimum u. So a minimum u is this. So when u is equal to u minimum, the v final is equals to 0, because any less than that, I do not have enough energy to reach to that high potential energy. Okay, so if I have enough kinetic energy, right, once I go to a high potential, any balance of energy can still be kept as kinetic energy. So the minimum is when just enough to reach at the height of 2r. So if it's just enough, that means I just have enough energy to become potential, nothing else. So Vf equals to 0. You know what I'm talking about, right? yeah, so I can explain again. So that means I want to, what is the minimum u to reach the distance of 2r? So u can be as large as you want, right? Then you can easily reach 2r, then you have some extra kinetic energy. So I want to find the minimum u in order to reach 2r. That means I want to have a kinetic energy, right, to reach the height of 2r. What happened? I need energy. How much energy do I need? I need energy to be equals to gmm over, well, I need the difference of this potential energy, so I need energy 2r minus gmm over r. Okay, so it's basically coming from this equation, right? So yeah, so for u is equal to u minimum, the v final is equal to 0. Any higher u, I can have higher kinetic energy. So in any case, I want to find mu minimum square, and then this equation over here, then this is 0, and then this is gmm over 2r. Okay, so the m everywhere has a m. I can cancel it. Then I have half u minimum square, and then I bring this over, so I got gm over r minus gm over 2r. So this is what? This is gm over r, 1 minus half, right? So 1 minus half, so I get another half. So I got half u minimum square is equals to gm half, so it's gm over 2r. So I can cancel the 2. So my minimum speed I need is gm over r square root. Okay. Yeah, hopefully that makes sense. Actually, it's the same conservation of energy from the high school, right? I'm just trying to express in a few different ways. Right. I mean, nothing quick lah. 1 minus half is half, right? So that's pretty much about it. So for this part is nothing special. Okay. So any other question? This is page 1, 2, and 3. Okay, so if everyone is okay, let us talk about the escape velocity next. Okay, so this is so yeah, basically we are talking about we have fancy equation, but it's just about energy, right? So energy, the total energy that you have is this much, right? Conservation of energy. So the total energy that you have can be kinetic, or you can use it for a potential, right? So if you're at a certain distance away from the center, then your potential energy must be a certain number. Then the balance can be used as a kinetic energy. So if you want to climb up to a higher potential, right? So if you're going to climb up to a higher potential, you need to reduce your kinetic energy, because k plus u must be constant, right? So so that is just by keeping track of the energy that you have. So the next thing I want to talk about is regarding the escape velocity. So what is the velocity that you need to escape the gravitational pull of a planet? Okay, so yeah, wait now, let's see. So let me write down the formula again for potential energy. Is gmm over r. Okay, and then from here we can calculate the magnitude of the force, right? So the magnitude of the force, well, the direction will be in the r direction, and if you remember, the magnitude of the force is obtained by differentiating r with respect to the variable, right? Differentiating u with respect to the variable. So if I differentiate this with respect to r, I get the magnitude as expected, okay, over r squared, right? So in this case, my positive direction is the direction of increasing r. Okay, so yeah, before I talk about escape velocity, right, I probably should spend more time exploring the potential energy function. So this is an inverse R, and then there's a negative sign. So the equation looks like this. Okay, so my function is actually like this. When R is very small number, U is a very negative number, right? So R cannot be 0 because you get a negative infinity potential. Like this, but as long as you're outside the planet, so let's say, yeah, I don't care what happens inside the planet, so I got this function over here, right? So this is my graph of my potential energy. So this is my U. Okay, so this is a graph of U. Okay, so let's say I'm at this position, right? So I'm at this position. Then what is the force experienced by a particle that is located in this position? You look at the derivative, right? So the derivative of this graph is this line. Okay, so the tangent line, right? So the tangent line, and the tangent line is positive, right? So the slope of this graph is a positive number, then the force should be the negative of this thing. So the force acting on it will point towards the origin, so the direction of F. Okay, so that's why when this graph is always having a positive slope. So if it's always having a positive slope, that's why the gravitational force is always pulling you towards the center, which is the big M, and that is how we get the direction of the force. The direction of the force is always pulling you towards the gravity of the source of gravity. Okay, so this part is pretty straightforward, right? Now, what do I mean when I talk about escaping? So notice that this graph, right, is asymptotic to the horizontal axis as r goes to infinity. So we notice that the gravitational force, in fact, right, the gravitational force is over r squared, and the slope will become flat only when r goes to infinity. So when r goes to infinity, the slope becomes flat, the force is 0, right? So when r is infinity, the force is 0. So only when the force is 0, that means at infinity, then the object do not feel the force of big M when it is infinitely far away, right? So you know what I'm talking about. Okay, so let me write this again. Gravitational force approaches 0 when r goes to infinity. So the reason why is we take the limit of r goes to infinity of my gravitational force is the same as taking the limit of r going to infinity of gmm over r square. And yeah, when r goes to infinity, this one goes to 0. So this will so am I recording? Yes. Am I recording? Test. Yes. So this will give us a definition of what does it mean by escaping the gravitational pull of an object. That means you can able to go to infinity, right? So the object M will escape from the gravity of M if it is able to reach R infinity. Okay, so that is what I mean, right? So this one is conservation of energy again. So let's say I'm initially at this position, let's say R1, right? So if I'm at R1, then at R1 my total energy of the system is half mv1 squared minus gmm over R1, right? And then I have some R final, so R2 over here, then my energy of the system is half mv2 squared minus gmm over R2. right? So I need to have enough energy to be able to reach this final R. And what if I want to go to infinity? That means I should be able to reach infinity. Okay, so so this is how we want to calculate this, right? So then this will give us an idea of how to calculate the notion of escape velocity. So let me talk about escape velocity. Okay, so let's say I'm talking about object M, all right, and then it's having the gravity by M, so by big M, but my initially, let's say it's initially at distance, some initial distance, right? It could be any number, but let's say I have some initial position, so let's call this big R, from away from my big M. Okay, so my position 1 is my big M is here, and then I have some distance R away from here, right? And then the speed of M, let's call this U. Okay, then I want to have my final position to be at infinity. So I want to talk about escape velocity. So what is the speed U to be able to reach infinity? Okay, so I need to final position. So it's infinitely far away. So R going to infinity. Right? So R going to infinity. So that means the by conservation of energy, right, is this. So the total energy in this situation is half m u square minus gmm over r square, right? And then the final position over here, the energy will be half mv square minus, well, gmm over infinity, so it's just half mv square, right? So this is the escape velocity situation that we want to calculate. Yeah, you're right. I keep writing square. The force is correct. The force is square. Potential energy is not square. Okay, so by conservation of energy, half mu square minus gmm over r, no square, is half mv square. And then if I'm at infinity, right, this is 0. Okay, so yeah, so we have the equation like this now. At position 1, the m is still under the force of gravity m, yes, and then r goes to infinity, just to say m reaches a distance. Yeah, well, they're both equivalent because only at infinity the force will go to 0. So I want to say r goes to infinity, right? Or in practice, when r is like very, very, very far away, like a few million light years, then it's more or less like infinity already. Okay, so again, right, as you can see, by conservation of energy, this one is some fixed initial position, right? So you need this much potential energy, and then it's like this. So it depends on your initial speed. So if your initial speed is high, right, then when you reach infinity, you have some extra kinetic energy, which can be going at velocity v. So I need to know what is my minimum velocity that you need to reach infinity. So minimum velocity, the minimum will correspond to where v is 0, right? Because if you have extra, then you have some extra energy. So what is the when my u is the minimum, the v is 0. So what is my escape velocity? So I got half mu minimum square minus gmm over r square over r, and then this part is 0. So and then also we realize that we can cancel m on both sides. I got u minimum square is equals to 2gm over r. Okay, So 2gmor, so the minimum velocity that you need is 2gmor square root. So this is the escape velocity. Velocity from the planet M starting at position R. Okay, so notice that if you are initially very close to the planet, you need a higher speed to escape. If you are initially very far away from the planet, then you need relatively less velocity to escape. Okay. Okay, so let me rephrase it in another way. This is the minimum speed required to escape from M starting from distance R away from M, and more specifically M's center. Okay, so the distance, of course, every time we assume it should be distance from the center of mass of M. So we should write at the center of the object. Okay, any questions so far? By the way, where's Zero is not here today. Why V0? Because minimum. Yeah, if V is not 0, right, then it's not minimum. I want to find what is the minimum speed that you need. Right? Let me tell you a stupid example. Let's say if you want to buy a PS5, right? And I don't know how much is the price of PS5. Let's put a random number, 1,000. Okay. So what is the minimum number that you need to buy a PS5? Like 1,000 ringgit. If you have 1,200 ringgit, fine, no problem, right? If you have 2,000, also never mind, right? So I need the minimum. So let's say, right, if you have 1,200 ringgit, right? Then you buy the PS5. So you buy already, then left with 200 ringgit. So you can use the 200 ringgit to do something else, right? So that's the extra thing. So this is the extra thing, right? I just need to escape the gravitational pull of the planet. So I just need to have enough velocity to escape from the gravity of the planet. So I put V0. Right? But let's say if I have higher kinetic energy than here, then by the time I reach to infinity, I have some energy left. Then this energy is used for kinetic energy, is used for the velocity. Yeah, everyone's sleepy today, is it? Well, not zero net force, because throughout the whole journey is experiencing the force from the big M. Zero other force. Yeah, because the whole story that we're talking about, right, is during the entire process, this M is experiencing the gravitational force away from the big M. Right? So as this goes away, the force can decrease and decrease, but still it's non-zero there. Yes, correct. R infinity implies F goes to 0. What does it mean? It means the total energy of the system. K plus U. I mean, conservation of energy, we've been doing this since initial energy of the system. And since energy is conserved, initial and final and intermediate values are always the same. Okay. Increase GPE and increase KE. Yeah, so as you can see, right, as the distance goes further and further away, the potential energy decrease, and this is a negative sign. So negative of, so as R goes larger and larger, right, this number becomes less negative. It approaches towards 0. So as R goes larger and larger, the potential is a negative number. So as R grows larger and larger, the potential energy increase. The potential energy increase, and therefore the kinetic energy have to decrease. So eventually, will it stop? Does it really escape, or just reaches a point where m is so that's why I was saying this calculation, right, the minimum. So if I start with this initial velocity, then eventually it will approach to, the velocity will approach 0 at infinity. So since it's at infinity already, then we are infinitely far away from the planet. So this is one way we can say we have escaped from the planet. Just barely escape, right? By the time you escape, you ran out of energy already, right? Just you totally run out of energy to escape. That's why we are calculating the minimum. Since we limit to 0, yeah, that's also another way to put it. Yeah, in the limit R to infinity, then the force limit goes to 0. Okay. What time is it? Okay, so let's calculate a simple example. Simple example is this 7.72. Escape velocity from Earth's surface. Okay, so nothing much to do here. Just give us a feeling of the numbers, right? So from Earth's surface. So starting from the surface of the Earth, what is the minimum velocity that you need to escape from the to escape from Earth, right? So the mass of the Earth, we have used this in Monday's class already, is 5.97 times 10 to the power 24 kg, and the rate, if you want to escape from the Earth's surface, so the Earth's surface is at 638 times 10 to the power 6 meters away from the center of the Earth, right? So 6,000 meters away from the center of the Earth. So my escape velocity is given by this formula. So let's see what happens if I put in all these numbers. So I got 6.67 times 10 to the minus 11. This is Newton's constant. The mass is 5.97 times 10 to the 24, and then dividing by distance. So 638 times 10 to the 6. Okay, so 10 to the 6. Then if I calculate all this number, I get 1.12 times 10 to the power 4 meters per second, right? And if I convert to kilometers, I get 11.2 kilometers per second. So you need to travel at 11.2 kilometers per second to order to completely escape from the gravity of the Earth. Okay, so that is the escape velocity from the Earth. So let's calculate another thing. Let's say I want to launch something that is inside our solar system. So if I launch a rocket from the solar system, right, the solar system is dominated by the gravity of the sun. So if I want to escape an object from the solar system, I need to escape from the gravity of the sun. So let's calculate escape velocity from the sun. From the sun, starting from Earth's orbit. Okay, so I have the sun, and the mass of the sun is, they usually use this symbol m dot, right, mc dot, and the mass of the sun is 1.9891 times 10 to the power 30 kg, and then the Earth's position is over here. So the distance from here to here is by definition is 1 astronomical unit, and it is given by, in SI unit, is 1.496 times 10 to the power 11 meters. So the escape velocity is the square root of 2 gm, and then the mass of the sun is 1.9891 times 10 to the power 30 kg, and dividing by this distance. So if I'm for a spaceship, spaceship starting from this distance, I need to escape from the solar system. I need to escape from this distance, and the velocity that you need is 6.449 times 10 to the power 6 meters per second. Okay. Any question? Yeah. Yeah. So an example of a, humans have launched spaceship away from the solar system before, like the Voyager 1, Voyager 2, and Pioneer 10 and Pioneer 11. So these are the 4 spaceship that has launched away from the solar system. Yeah, Voyager. You said that it reminds me of the Neon Cat in the space, the animation, something like that. So another interesting thing about Voyager, right, is in case, have you heard about the Voyager spaceship? Like, in case got alien come across the Voyager spaceship, because Voyager is going away from the solar system, it's going very, very far away. So what they are thinking is, in case got alien come across to the Voyager spaceship, then they put a message to the alien. So the humans, so they put something on the Earth, and then they put all the information about humans on the Earth. They put some music there. They put the diagrams of how the human look like, a man and woman, and then they put the location of our solar system. They put something on the spaceship, and then they launch. Yeah, so I don't know if you heard of it, or if you don't know what I'm talking about. The golden disc. The golden disc. Yeah, so the picture is like the one naked man and one naked woman. So yeah, that's why people are saying what if the aliens see this and then they come to attack. Yes, they need to solve the code, because that's the problem, right? We don't know what language the alien are speaking, and then human also can only speak human language. So they try to like draw a diagram that is the best way, most likely they can understand. The Da Vinci Code, they put the Vitruvian. Yeah, I think they put the Da Vinci Code picture also. Correct, math is universal, but our math notation is not. That is also another thing. For example, right, I was like talking about this with a colleague from MAT lah, Dr. Chang Ching Hao. It's like, because he said lah, humans use math, right? We use notation. We calculate numbers 1 to 10, and our calculation is like base 10, correct? So our notation is like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And then after 10, then we repeat the symbols, and then 19, and then 20, and then 21, and then like this. And the main reason why we have this, right, is that we have 10 fingers. So we use a base 10 notation. What if the alien, right, got like 7 fingers or something? Then the numbers they use will be different. Yeah. Well, right now we don't know, right? We don't know. Yeah, they can play piano very well. Yeah, so right now we don't know whether aliens exist or not. We haven't discovered any. But most likely the universe is so big, so it's quite likely to exist. So what Dr. Chang was saying, right, he was talking about the movie Arrival. In the Arrival movie, right, the alien has 3 limbs, and each limb have 3 fingers. I think something like that, right? I forget. But what Dr. Chang was saying is, because that 3 and 3, right, their numbers may not use a linear system. They might use a logarithm of base 3, if such a alien might exist. Yeah, ET also got 3 fingers, correct? Yellow. Yeah, Fermi paradox. The Fermi equation. Okay. What time is it now? Fermi paradox. No need to chop, because we just want to communicate numbers only, right? Yeah. So one last thing to talk about escape velocity is I should at least mention the first time we encounter the concept of black hole is when, if the escape velocity equals to the speed of light. Okay, so what happens if my escape velocity is equals to the speed of light? So it's gmm over r. Okay, so this is where we learn about the concept of black holes for the first time. Is that the escape velocity equation, right, it depends on m over r. So it's kind of like depends on the density of the object. So if the m is very high, the escape velocity is very high, right? Let's say from fixed r. So let's say r for like 10 kilometers, but if m is very high, the velocity is very high. So if m is even higher, the escape velocity becomes even higher. So eventually we will come to a point where the speed of light is your escape velocity, and if your escape velocity is the speed of light, then you totally cannot escape. So it becomes the black hole. So but for now, right, let me solve this for r. Okay, so if I solve this for r, I just get 2gm over c square, right? So let's calculate what is the distance to escape from the sun. So for the mass of the sun, right, the distance is 6.67 times 10 to the minus 11, and then the mass of the sun just now I wrote down, right, so 9.98191 times 10 to the 30, and then if I compute the speed of light square, speed of light is just 3 times 10 to the power of 8 square, so you get 2948 meters. So this is 2.948 kilometers. So if I have the mass of the sun compressed into a radius of 2948 kilometers, I can create a black hole, right? So if I can, because if the distance is 2.948 kilometers and the mass is the mass of the sun, the escape velocity is going to be the speed of light. So that means if the mass of the sun is compressed to such a small size, it becomes a black hole. Actually, no. Not really, but somehow it gives the correct radius. Yeah, so this is the structural radius. It happens to give the definition of the structural radius. But Eric, you're right. I was kind of like taking a shortcut, because if we are talking about black hole, right, we should talk about relativity. So in relativity, we cannot use this equation for kinetic energy anymore. The Fermi paradox, yeah, is a statistical problem. So yeah, so if you estimate the probability of like civilization happen, you actually get probability close to 1. Because nothing can travel faster than light, or nothing can even reach the speed of light. Light is the fastest object. So if your escape velocity is higher than the speed of light, then you cannot escape already. Yeah, can. That's why you have black holes. Okay, so yeah, by the way, now is a good time to take a 10-minute break. So but you can continue to type in questions, but I should stop the recording and rest for 10 minutes, and then we continue the tutorial after this. Recording and start recording. Black hole absorb things, yes, which is why we say that once you fall inside, you cannot come out anymore. His third law need imagination, yes. Yeah, he need to come up with free body diagram and then the normal force and this thing. There is, yes. Yeah, so there's a branch in philosophy that is connecting to physics, and yeah, I can share a lot of they write a lot of interesting papers about this. Has physics reached a point where philosophy doesn't help? Not really. I mean, it's hard to say. You can say yes and no, because there's a lot of questions, a lot of results in physics that philosophy actually doesn't know how to explain, like quantum mechanics, quantum mechanics, in some sense relativity and quantum gravity. Yeah, and it's not really philosophy doesn't understand, but based on this result, can you come up with a philosophical explanation of why these things are happening? That is what people are trying to do. Physics can shape the philosophy. Can you do that? Yeah, I think Zuri will be interested in things like this. Philosophy of physics. Yeah, you can look up a lot of interesting questions. If I remember, maybe I will post some of the articles here. Yeah, so for now, yeah, like Berkeley's determinism. I'm trying to remember all the interesting stuff I came across. I don't know how to find it. I'll try to find them again, and then I will post it if I can find it. But for now, let us do tutorial 6. Yeah, so if you remember, right, tutorial 6 was about, chapter 6, it was about angular momentum, rotation, and torque. Right, so let us see. Yeah, so let me talk about this first before we run out of time. I will read the questions later. Okay, so let's start with question 1. I have a dog of mass m, right, standing on a turntable. So this thing can rotate. So like something kids can play on a playground. So if you walk on the rotating turntable, right, the table itself will rotate in the opposite direction, and the main reason is to conserve angular momentum. Okay, so how do we solve this? I will upload the solutions later once we're done, but we want to calculate. Okay, so if the dog walks one full circle with respect to after the dog one full circle on the table, what is the fraction of the angular displacement of the dog? Okay, so let us try to solve this problem. So let me write the initial position of the dog. So initial position of the dog is over here, right? And then after the dog walks one round on the table, so the table has some initial position, right? So so the dog will walk one round, right? So if the dog is walking this way, the table will turn the other way, right, to conserve energy. So if the dog is walking in this direction, the table will turn in this direction, and then the dog keeps on walking until he comes back to its initial point on the table, right? So what is the total angular displacement? So the dog will rotate by some angle theta dog, and the table will rotate by the angle theta table. So angular displacement of the dog okay, so theta dog. I haven't decided what is clockwise, what is anti-clockwise yet. So let me just say the magnitude. So it's equals to theta, right? And then angular displacement of table. I talk about, so it's some number theta dog and it's some number theta table. Okay. But if you look at this picture, right, the dog walks one round until he comes back to the starting point of the table. So from this picture, do you agree that whatever this angle is plus this angle is, it will be equal to one full circle, 360 degrees? Okay, so this is the important realization. And once you accept this, then the rest is just continuing with the calculation only. Yeah, you absorb everything, and then we got the Hawking information paradox and all this kind of thing. Oh, cool. Application of philosophy. Yeah, so people do tend to jump between philosophy and physics, like jump forward and jump backward. When I was a student, right, there's a teaching assistant. He did a bachelor in physics, and then he worked as a teaching assistant, and then he taught my class for a while, and then after that he continued master in philosophy in the US, I think. Yeah. But so everyone is okay with this, huh? So if everyone is okay with this, then I'm going to use conservation of angular momentum. Okay, so firstly we will assume constant velocity. Okay, and then I'm going to use conservation of angular momentum. I'm lazy to write the full sentence, but so initially is at rest. Everybody is at rest. So initially the total angular momentum of the system is 0. So I got 0 over here, and then these two things are moving in circular motion. So I have a table where my moment of inertia is I. And then let me just write this angular momentum of the table. So angular momentum table, and then plus angular momentum of dog. Okay, so the angular momentum of the table is I times omega table, and then the angular momentum is moment of inertia of the dog plus theta omega dog, sorry. Okay. Wow, so cute. Yeah, so that's basically the situation like this, right? So how do we solve this problem? All right, so I think everyone is okay. This is nothing but conservation of angular momentum. Initially, everybody is at rest, so initial angular momentum 0. If the dog starts walking one way, the table will turn the other way in response to make sure the total is still 0. So when the dog is walking, what's going to happen? It's going to walk at some angular velocity here and angular displacement here. Now, as the table rotates, right? So let me say anti-clockwise to be positive. So if anti-clockwise is positive, then the table will be rotating in a positive direction. So I will have a positive number, and then what is omega? Omega is just the angular displacement table divided by the time taken. Okay, and the time taken is actually not important. And then for the dog, right? Okay, what's the equation for the dog? For the dog, the moment of inertia of the dog is what? mr squared, right? If we treat the dog as a point particle at the distance r away from the center. What is the angular velocity of the dog? Angular velocity of the dog is going this way. Okay, so the dog is going this way and it is clockwise. So it is clockwise, so it is the opposite direction of anti-clockwise, so it's negative, right? And angular velocity is just the theta dot magnitude divided by the time taken. But actually the time is not important. So I got I theta table magnitude minus mr squared theta dot magnitude. Follow so far? So now, based on this equation, right, we say that, well, I have two variables and I have two unknowns, so I can eliminate one of them. So we recognize that theta table is just 2 pi minus the magnitude of theta dot. So I can substitute this into here. So 0 is I, 2 pi minus theta dot minus mr squared theta dot. Okay, so I simplify, so I got 2 pi I minus I theta dot minus mr squared theta dot. So I bring the theta dot terms over here, so I got I plus mr squared theta dot is equals to 2 pi I. So theta dot is 2 pi I over I plus mr squared. So that gives us the angular rotation of the dot, and then I want to calculate the fraction of the circle. So how much is the dot angular displacement over one full circle? So that is given by I over I plus mr squared. Okay. So I don't know whether you guys are following this. Hopefully this is understandable, and I believe the key step is here. So once you recognize this, right, then the rest is just to apply. I hope everyone find this part is logical. The table rotates one way, though the dot goes the other way, so one is positive, one is negative. The dot and the table turn, yeah, correct. So why, right? Because the question say the dot walks once around the circumference of the turntable. Yeah, so this question is a bit unclear lah. But don't worry, the quiz and exam, they won't ask unclear one, right? So the dot walks once around the circumference of the turntable. So that means, that's why I put the flag. So the dot starts at one point on the turntable, then he will keep on walking until he come across the flag again, right? And then the turntable rotates this the other way. Okay, so if you walk this way, right, that means the dot will cover the circumference of the turntable. Yeah, you can use the right hand rule, but I think this is easier, right? Because you don't really need the right hand rule. You just know, all we need to know is one is positive, one is negative. They are just two directions. So one right hand rule is one axis is going up, then the other axis is going down. And then the equation just give you the negative sign. One is positive, one is negative only. Yeah, yeah, not necessary. Just yes, correct. Just opposite direction is enough. Okay. Yeah, so let's do another question. If the dot covers the circumference, so it is only 360 degrees relative to the turntable, but with respect to the ground is less than 360 degrees. The last part, just the manipulation part. This part. Right, so it's relative to the ground and then relative to the table. Okay, done. Okay, what shall we do next? Maybe we do question 3. I believe question 3 is fine. Question 3 is the tricky one. Can you use where is it? Can you use relative motion? You can, but not in the one that we learned in chapter 1, right? Because this is a rotational motion. So if you want to express your formula, it's a bit messy lah. Can you use it? I mean, you can. Then you need to use a lot of vectors because we are talking about vector now. Yeah, and not just vector, rotation. So our relative we derive it for the case of Cartesian coordinates, x, y, z coordinates. But for rotation, it's not very convenient to use x, y, z, right? Because it's circular motion. Not to say impossible, but very messy if you use relative velocity. Okay. Sum of angular distance. Yeah, so angular distance 2 pi, you can, but it will be better if you use polar coordinates, the polar coordinates. Rotation is a bit complicated in math, definitely, because if you go straight line, then everything x, y, z, no problem. But then if you have rotation, right, then you need to draw circles, then equations of circles or angles and things. Very messy. Very complicated. Actually, it's not complicated. It's easy once you change to polar coordinates, just that you haven't really learned polar coordinates yet. Once you learn polar coordinates, then you can do it. I think you can. You try and see lah. I have not tried myself. Should be possible. Should be possible, I believe. Yeah. Because you just need to focus on the distance traveled and then the speeds. Well, for Eric's case, if you only focus on displacement, yes, but yeah, it doesn't capture the information about centripetal force. But this question doesn't have centripetal force, so that's why still can. Okay, so question 3 is this. right? Like this, right? Yeah. Yeah, right? Question 3. Okay, so we have a thin uniform. Did I record? I'm recording, right? Yes. So I have a thin uniform rectangle sign hanging vertically above the door of a shop. So yeah, the tricky question is usually, right, these are taken from textbooks and things, and especially American textbooks where everyone's English is very good. So you have all these weird sentences. So don't panic, right? Just, we are here to learn the physics. So let me help you explain the problem here. So basically the picture is at the end of the day is like this. So I have a rectangle, and then I have the if it's a rectangle and it's hinged at this, right, then it's basically like a rod of length L, right? So this is L half, and then this is L half, and then the mass is given. So if this is a rod, right, the moment of inertia hinged at the edge is 1/3 ml square. The mass is 2.4 kg. The length of the whole thing is 0.500 meters, 0.05, so 50 cm, right? So this is basically what all this is saying. The sign is swinging without friction. Initial angle 25 degrees to the vertical. So initial angle 25 degrees means 25 degrees initially here, and then it swings down, right? So it swings down, and then at the moment when the sign is vertical and moving to the left, so at the moment the sign is vertical and moving to the left is over here, right? So if it's swinging, then it has some velocity, so I got angular velocity. So this is the moment where the sign is vertical. Okay, so what are we supposed to find? Well, there's a snowball, right? So there's a snowball of mass 400 grams. So small m equals to 400 grams coming in from the left, and then it hits the sign, right? And we know the initial velocity. So the initial velocity is 1.60 meters per second. Okay, so this is 0.4 kg. Okay. So firstly, part A is calculate the angular speed of the sign immediately before impact. So I want to calculate what is this omega. Okay, so let us calculate this omega. We are going to use conservation of energy. So initially my object is here. So will be more convenient if I just look at the center of mass. So initially my center of mass is at this height. Later it's at this height, so the potential will convert into kinetic energy. So initially it's at rest, right? So firstly I can calculate the change in height of center of mass. How do I calculate the change in height, right? So I just need to know what is the change in height, right? So what is the change in height? Well, I can easily calculate, right? The full length here is L half, and then this part should be, well, on this side is still L half, and then I cos 25. So do you agree that the change in height from here to here is L half minus L half cos 25? Okay, do you agree? L over 2, 1 minus cos 25. So no objection, right? So the change in height is given by this formula. Once I know the change in height, then the rest is very easy. Conservation of energy. So the change in potential energy will be converted into the kinetic energy. So half I omega squared. So since there's going to be some later omega, so I'm going to call this omega 0. Right? So the change in potential energy will become the rotation of the rod. This is big M, sorry, big M. Okay, everyone is following, right? Then the rest is just, yeah, put in our numbers. So my moment of inertia is 1/3 ml3. ml square, and then the omega 0 is what we want to calculate. So the h, actually the h is here, so we put the h into here. Then let's see what we have. So mg, the h is half L 1 minus cosine 25, and then this is well, half and then 1/3, and then ml square omega square. So I can do some cancellation. Half half, 1L cancel with 1L here, and then the 3 I bring there, so I got G 1 minus cos 25, and then on this side is L omega 0 square. So omega 0 is what? Well, omega square is going to be 3G over L 1 minus cos 25 degrees. So G is 9.8, L is this, so I can compute omega 0. So omega 0 is 2.35 radians per second. Okay. We already considered, because this is the rotational kinetic energy of the whole thing. Yeah. So if you want to consider, if you want to still treat as a center of mass, right? Then we do it this way. So this VCM is the center of mass of is this thing over here. So it's the tangential speed at the rotation. Actually cannot because this is not a free yeah, it's not a free actually cannot, I'm not sure. The safer way is to just treat it like, because you got omega, so just take omega just like that. Yeah, so better not to do it this way, because the reason why I say not, right, because I'm not sure. This is like a constrained motion, so I need to think about all the factors to make sure that the energy is conserved completely over here. But if you treat it like a rotating object, then yeah, the change in potential energy will be gained in the rotational kinetic energy because it is a rotation. Then yeah. Okay, so I got my omega now, and then the next part is angular speed immediately after the impact. This, we are talking about the snowball, because as the thing is, as the sun is coming down, right? As the sun is coming down, there's a snowball that impact with it, and then it stick to the door, right? So it stick to the door. So this is a collision, and I can treat this as a conservation of momentum problem, and I'll try to solve it this way. But since we are talking about rotating systems, right, I will use conservation of angular momentum. Okay, so this is a collision. This is part B. We are talking about collision among rotating systems. So let's look at before collision, and then let's look at after collision. Okay, so before, right, is the instant before, just before, because we have calculated the omega just before. Okay, so just before collision, and then this ball is coming over here, 1.60, right, and then the mass is given. Okay, then after collision, well, after collision is, then maybe they stick together, moving as one object, and then the omega final. Okay, so how do we solve this? We are talking about before and after, so we are using conservation of angular momentum. So that means the total angular momentum before collision is equals to total angular momentum after collision. So what's the total angular momentum before collision? Before collision, right, I have two things, this thing and this rod. So there's a snowball and there's the rod. So the angular momentum of snowball and then angular momentum of the rod, and then after collision is rod and ball moving together. Okay, right? Everyone agree with this description, right? So let's calculate the total angular momentum one by one. So this is a snowball moving linearly at velocity u. So I have the linear momentum mu. But given an axis, I can calculate the perpendicular distance to get the angular momentum. So the angular momentum is, the distance is just L, so it's MUL. Right? Angular momentum of a point particle is just the linear momentum times the distance from the axis. Right? How about rod? Rod is I omega. The rod is going at omega 0, which we calculated to be 2.35. So I will put in the numbers later. And then rod and ball moving together, so I will have the total moment of inertia times the omega final after collision. Okay. By the way, I forgot another important thing is that I forget to describe the sign. So one of them should be negative. Okay, and why? I must remember to put in the negative sign because the axis is here, right? So this ball is kind of like going in the anti-clockwise direction, but the rod is in the opposite direction. So these two are moving opposite rotation. So if I call clockwise to be positive, then the doll will have positive angular momentum. The bullet will have negative angular momentum. They are opposite directions. Okay? Follow so far? Huh? Right? So let's put in the numbers. M times U times L. So all these three values are given. So if you calculate everything together is 0.32. Right, and then the moment of inertia is just half ml square omega 0, and then the total moment of inertia is 1/3 ml square, and then moment of inertia of the snowball is just at a distance of L square, mass times distance. Right, so you get 0.032, 1/3. What number did I put? So 1/3 ml square is going to be 0.2. Omega is 2.35, which we just calculated. So this is going to be 0.2. This is going to be 0.1 omega final. So we can use this to calculate my omega final, which is 0.50 radians per second. Okay, I forgot to put a negative sign. So did I cause anyone to be confused? So let me check. This one was just now, right? Yeah. So everyone is okay. The B. Starting from where? Well, basically, the basic idea is conservation of angular momentum, right? Before collision, after collision. So this is I want to calculate by conservation of angular momentum. Total momentum before collision should be equal to after. There is no external force or external torque, right? So yeah, I'm talking about angular momentum. So what is the total angular momentum before collision? I have the ball and the rod, the snowball and the thing here. So this plus this. After collision, they stick and move together, right? So for snowball, right, the snowball is traveling to the right. the axis is over here. So this is having the ball is having a anti-clockwise direction. So I got negative sign over here. And then what's the formula for angular momentum of a point particle at a distance L from the axis? It is mu times L, right? So linear momentum times L. So this is the formula for angular momentum. We talked about this in chapter 5. Yeah, no, 6, right? And then the rod is just I omega, right? And then the I omega, basically the moment of inertia of a rod hanging from the end is 1/3 ml squared, right? We spent so much time deriving this. And then when they move together, you just sum up the moment of inertia of each of them, right? So we got this, so we got both sides of the equation. And then once you plug in the numbers, you find omega final. Okay. Okay. So what time is it now? Wow, 5 more minutes. So let's do the last part. So the last part is to say that what is the maximum angle the sign will swing after impact. By the way, my omega final is a positive number. And just now I was saying, you know, when we started the calculation, my positive is clockwise, so it swings clockwise after collision. So this is the situation that we want to solve now. So in part C, right, just after collision, I have the rod, I have a snowball, right, and I have calculated my omega to be a positive number. So according to my direction, it is swinging this way after collision, right? And then this is just after collision. And then what happens after next? I want to calculate when it swings to maximum height. Okay, so after it collide, right, it will swing. So how high up does it swing? We want to find the angle or what? Yeah, the angle. Okay, so how do we solve this question? So if you want to talk about height, right, then it will be easy to use the concept of potential energy. So to get the potential energy, it will be easy if we can find the center of mass of the combined system, right? So I have the center of mass of rod, which is the distance x1, and then this is x2, right? I want to find the new center of mass of the total system. Okay, so once I find the new center of mass of the total system, I can find out the change in the height of the center of mass. Okay, so let's find the center of mass of the total system. So my xcm, okay, is this. So so let's say this part is x equals to 0, right? So I want to find what is the distance from the axis. So according to the center of mass, I have the mass times position 1, the other mass times position 2, divided by the total mass, right? So the mass of the rod is 2.4. The position is, this is a uniform rod, so it's L half. So it's L half, so it's 0.5 over 2. The mass of the snowball is 0.4. The distance from here is just the total L, so it's 0.5. And then m, big M plus small m. So my center of mass of the system is at 0.2857 meters. So that means this okay. So now we can calculate the change in the height. Center of mass. So the change in the height of the center of mass is supposed to be x. Well, we do the same method that we calculated just now, right? So from here to here is the xcm. Then from here to here is xcm cos of the angle. So it's xcm minus xcm cos of the unknown angle. So I don't know what is this angle. So xcm 1 minus cosine of the angle. Okay, so this is the change of the height. So now we can use the conservation of energy. Right. So my energy at this state is half I omega final square, and then by the time it reaches here, it swings until rest. So it will all the rotational energy will be converted into potential energy. So I want to calculate the final height, right? So then let's work out left and right hand side. So the moment of inertia of the total system is just moment of inertia of the rod plus moment of inertia of the snowball away from the axis. Omega square we calculated in the previous part is 0.5, and then this one is just the sum of the two masses which we know already, and then we put in this h to be here. So I got xcm 1 minus cos phi, right? So all these are numbers, so you can put in to calculate. We just now, right, we had calculated 1/3 ml squared to be 0.2, this is 0.1, this is 0.5, we got this previously. 2.4 plus 0.4 is 2.8, g is 9.8, xcm is 0.2857, and then I got 1 minus cos phi. So we try to get cosine phi from here, right? So what I got is 1 minus cos phi is, based on calculator, is this one. So cos phi is 0.9952, so phi is 5.60 degrees, like this. Okay, any question? No, Jiacheng, the mosquito is not slain. I didn't get it. I didn't catch the mosquito. Yeah, so no question. Okay, so if not, then yeah, we're just about we ran out of time. So I think that should be all for today. Okay, so in the next week's tutorial, next Wednesday, right? Next Wednesday, I definitely will do this question. I think this question is similar to the final example of chapter 6. So if you know how to do that, then maybe you can do this. Okay, and then this part is also a bit tricky for most students. So next Wednesday, I will probably do these two questions. Okay. Yeah, besides that, if there's no other question, that's all for today, right? So I will, everyone okay? Okay, so no question, then yeah, thanks. That's all for today. The car or Linux better than the Windows, is it? You mean this one? Is it? I don't know the Windows version. But yeah, I really like the Linux cow. Which part you don't understand? When will the finals be? Usually the date is set by the office, and they didn't they will announce it closer to the end of the semester. Why have two center of mass? Because I have two objects, a snowball and the door. I have a snowball sticking to the door. The door originally has center of mass right at the center, right, L half. And then the snowball is a snowball. So I have two masses. So two masses, if I stick them together, what's the center of mass of the combined system? Yeah. Well, the final will be, I think the final is like what, 7 weeks away? Still got some time. If the snowball stick to the center of mass of the door, then the center of mass is still the same at the center. Actually, I don't know. What week is it now? Now is week 9. Yeah. Our last lesson is week 15. Week 15. Oh, it's less than 7, I think. So 6 weeks to the last lesson. And then depends on when is the exam. Yeah. Don't know what date they put the exam. Now it's week 9, yes. Yeah, probably not too hard. So because the last few chapters is pretty much, you know, here and there. Actually, yeah, you're right. If you look at the mass of the snowball, right, is quite small compared to yeah, so if you look at it, right, original cm of door only, a rod only, right, is L half. So L half is 0.5 over 2, so it's 0.25. So it only changed by a little bit only. It's a sticky ball, not a snowball. Like a pancake. Is it very fast, Sohan? Sticky ball. Yes, correct. Based on our calculation, it continues to move clockwise. So it slapped the door, and then because if the door is too heavy, right, the door is like moving too heavy, so it slapped the door, and then the door continues to push everything in the clockwise direction. Yeah. So who got stay in a place with snow before? I don't know lah, whether this is true or not. If you throw a snowball to a door, can it stick? Slime. Yeah, we can change the question to a sticky slime ball that will stick to the door. The moment of inertia, yes, because if it's attached to the door, right, then anything after that, the snowball is always at distance L from the axis already. Never seen snow in the entire life. Huh? Me too. Artificial snow got lah. Wow, north of China get to play with snow, right? Yeah, but then you have to survive cold weather also. It will just splat and the bits will stick to the door. Yeah, I imagine that's what happened, right? By the way, I forgot. Was there snow in New Zealand, Dr. Gloria? Don't think so, right? You're not. Are you fast? There was. Ooh. So jealous. Yeah, that's the snow that we get in the freezer. Oh, only for one day. Yeah, that's true. Snow is like mostly water, but sometimes you can, even in the freezer, right, in your fridge, the ice part, if you put your hand, you can feel like it's a bit sticky if it's cold enough. Yeah, maybe. Yeah, if you see the movie Dumb and Dumber, right? Apparently, if you lick a frozen surface, your tongue will get stuck to it. I think it happens like if you lick ice also, you will get stuck to it. It's a bit sticky. Okay, by the way, for everyone else, yeah, if you want to leave, that's all for today. We finished all the questions already. So we will continue the other topics on the, continue talking about gravity on Monday. So, but Monday we will go to a bit of a calculus type of stuff again. Yeah, so I'll see you on Monday. Snow will fall to the ground and form a nice thick cushion. Oh. Ah, is it? So you cannot form snowballs. It's not cold enough to make snowballs in Christchurch. Yeah, it depends on the surface of the door also. That is also true. So maybe for a certain type of door you can make it stick. Oh really? Got this one? Wow. Talk about this. This should be quite interesting. ml square is the moment of inertia of the snowball. Mass times distance square. That's it. I think you have to look at chapter 5. Yeah. I don't think it's just mass times distance square. That's it. We talked about this in chapter 5, but we hardly ever derive it again. We just use the formula only. What's this? Oh, I can't open this file. Oh, by the way, I'm still recording, is it? Let me stop the recording.